In this problem on work and energy, we are told that a sled with a given mass starts up an incline with a given speed. We are also given the coefficient of friction and asked to calculate firstly how far up the incline the sled will travel, the condition that must be placed on the coefficient of static friction so that the sled does not get stuck at its highest point, as well as the speed that the sled will return back to its starting point. So firstly, we'll have a look at our diagram. So we have a frictional force acting down the slope, the normal force acting perpendicular to the slope, as well as the weight acting vertically downwards. Now, from this free body diagram, we can see that the sum of the forces acting on the sled in our y direction is equal to the normal force Fn minus the component of the weight perpendicular to the plane, which is mg cos theta, and that's equal to 0. And so from here we can see, therefore, that the normal force Fn balances the component of the weight perpendicular to the plane. So Fn is equal to mg cos theta. There's no motion in our y direction. And therefore, the frictional force Fr is equal to the coefficient of kinetic friction mu k times mg times the cosine of theta. So that's the frictional force acting parallel to the plane. So we can apply the conservation of energy with a frictional force, and we'll use subscript 1 to refer to the sled at the start of the motion, and subscript 2 refers to the sled at the top of its motion. So if we take the starting position to be the 0 for gravitational potential energy, we have V1 is equal to 2.4 meters per second, y1 is equal to 0, and the final velocity at the top of its motion, v2, is equal to 0. So we know that y2, its final position, is equal to d sine theta. And we need to solve for d, where d is the distance it travels up the slope. So using the conservation of energy, we have conservation of work and energy. The initial energy E1 is equal to the final mechanical energy plus the work done against friction, which is the frictional force times the distance the sled travels d. And so this implies a half m v1 squared plus mg y1 is equal to the final kinetic energy, a half m v2 squared plus mg y2 plus the work done against friction, F friction times d. So if we rearrange this equation and remember that the initial position y1 is 0 and the final velocity v2 is 0, we can solve for the distance up the slope d, and d is v1 squared divided by 2g into sine theta plus the coefficient of kinetic friction mu k times cosine of theta. And these values are all known, so we can calculate d. So this is the initial velocity, 2.3 meters per second, and that's squared, divided by 2 times the gravitational acceleration, 9.8 meters per square second, times the sine of 28 degrees plus 0.25 cosine 28 degrees. And so if we calculate this, we get the distance traveled up the slope to be 0.3910 meters. And if we keep our significant figures, this is 0.39 meters. So that's our first answer for part A. Now, for part B, we want to find the condition that must be placed on the coefficient of static friction to prevent the sled from getting stuck at its highest point. Now, for the sled to slide back down, the friction force will now point up the hill in the free body diagram. And in order for the sled to slide down, the component of gravity along the hill must be larger than the maximum force of static friction. So this means mg sine theta must be greater than the frictional force, which means that mg sine theta must be greater than mu s times mg times the cosine of theta. And so rearranging this, we see that the coefficient of static friction, mu s, must be less than the tan of 28 degrees. And therefore, the coefficient of static friction has the restraint that it has to be less than 0.53. And then we've placed a restraint on the coefficient of static friction so that the sled will slide back down after reaching its maximum distance up the slope. Now finally, in part C, if the sled slides back down, we want to know its speed when it returns to its starting point. So we can again apply the conservation of energy and include the work done by friction. But subscript 1 this time refers to the sled at the top of the incline, and subscript 2 will refer to the sled at the bottom of the incline. So we know that in this case, v1 is equal to 0, y1 is equal to d sine theta, and y2 will obviously equal to 0 at the bottom of the hill. So again, applying the conservation of energy, we have that E1 is equal to E2 plus the work done by friction, which is the frictional force, times the distance d. So this can be written as a half mv1 squared, the initial kinetic energy, plus the initial potential energy, which is mgy1, must equal to the final kinetic energy, a half mv2 squared, plus mgy2 plus the work done against friction, F times d. Now we want to solve for v2 in this problem. So if we rearrange and substitute our values, we get v2. Remember, v1 is equal to 0 as well as y2. So v2 is equal to 2 times the square root, or the square root rather, of 2 times gd into sine theta minus mu k cosine theta. And so now we can put our values into this, and this is the square root of 2 times 9.8 meters per square second, let's suppress the units here, times d, which is 0.3910, times the sine of 28 degrees minus 0.25 cosine 28 degrees. And so we get the final velocity when the sled reaches its position at the bottom of the hill to be 1.4 meters per second.